So today's slide will be about like PageRank, which is like algorithm used by Google for information retrieval, where you have to extract links. In this slide, we extract link from Wikipedia and build what we call the Google matrix. Google matrix is like we can represent pages as directed as a graph, where if there's a link between one page to another page, we consider this as a connection between nodes in the graph. And the goal is like to build like ranking based of repetition, as if you have like one page that is connected to some pages and the page has like high repetition. This repetition should be like spread out between all the other pages that are connected to that page. And let's have a small visual. Let me check this one. So this means basically that we can have like, if you have 3 pages, we have page A, have another page, page B, and one last page, which is page C. And there's a link from page A to page B, from page B to page A, from page A to page C, and from C to A. And also we have one link here. All right. So each of these pages will have like repetitions. Like let's say repetition of, we note it as R. So we have RA, RB, and RC. And we can represent like we can compute the repetition of each page I as the sum of the repetition, because the repetition of one page, if highly repeated pages links to a given page, this means that this will improve the repetition of that page as well. So we compute this as all pages where we have the incident links to this page, where we take the repetition of that page divided by the number of the outgoing degree of that given page. So basically this means that the repetition of this page will spread out to all outgoing pages. And also the same here.
What was the RI again?
It's like a repetition of the page.
And like if we have any loops, it's considered as one, right?
Yeah. So how are we going to build it? So if we compute the repetition of A, because this is a problem where you have pages that are interconnected, also those pages are having repetitions, but we want to rank those pages based on the fact that if one page is highly repeated and receive connection from other highly repeated pages, it increases the repetition of that page also. So we compute the final repetition of A based on the repetition of the pages that are connected to A. So following this formula, from the repetition of A, we will see that A receives connection from share. It receives connection. It receives connection from B and from C. So it will be based on the repetition of A and of B and C. So we will write it as the repetition of B divided by the number of outgoing links from B. Because if B is highly repeated, the repetition of B will spread out to all the pages that are that we can access from B. So that's why we divide by the outgoing degree of B. What is the outgoing degree of B here? We have 2, right? Because we have 2 nodes that we can reach from B. And plus, what the second node, which is connected to which is going to A, we have the node C. So it also takes like the repetition of C divided by the out degree of C. So C has only one out degree. So this means that all the repetition of C will spread out directly to A. So finally, we have just here plus RC. In the same way, we compute
RB, sorry, how did we calculate RB? I mean, how do we have RB?
Yeah, we compute RB in the same manner. So we will finally have like a question, a system of equation that have to solve to find the repetition of those pages and rank them based on that information. Is it clear? That makes sense?
Yeah, I get it.
Yeah. So to compute repetition of B, you also look at the incoming links to B. So we have from A only, have this only, right? So repetition of B will be equal to over 2. Over 2, yeah. And finally, we have the repetition of C, which will be equal to?
It will be equal to RA over 2 and RB over 2.
Exactly. So we have here RA over 2 plus RB over 2. Well, so then we can have like, from these things, we can have like system of equation when you need to find A, B, and C. We can also represent this as like matrix representation, where we can break it into a matrix M and a matrix, the matrix R. So we can take the vector matrix R as just the vector where we have all the repetitions like RA, RB, and RC. And then we can represent the matrix M as the adjacent matrix. So where we have MIG is equal to 1 divided by the out degree of A if there is a node from G to I and 0 else, right? So this means that we can rewrite this as R MR. But what is M in this case? We can define M based on the information that we have here, right? So we can rewrite M as, so here the first component here is 0 because there's not a link from A to A. So we can
so we have MR, R is the vector of our like RA, RB, RC, and MIG
and M is the
adjacent matrix.
Yeah. So we can represent it as the same equation. So we can represent this system like this, right? Now we need to come out with the M. So M will be, so here the second component you have there, 1 divided by 2. As we say, we divide by the degree, out degree from I, right? And here we have what, 1. The second row, we have here 1 over 2, and here 0 and 0, right? And the last row, we have 1 over 2, 1 over 2, and 0. So here's our matrix M, and here's the matrix R, right? So, so we need to solve this to come up with the solution of those the final repetitions. So where the repetition will spread out between each other, and then we need to find the page that we have that has repetitions. So this is basically how Google does like to give the final ranking, right? So how can we solve this? We can solve this like using a straightforward way, like we can try to solve it like using algebra representation. Or if you take a look at this, you will see that the matrix M has a property, very interesting property, where it is column stochastic. This means that if you sum up the value in each column, it gives 1, right?
Yes.
Since M is column stochastic, we can then apply like the Markov chain rules to find the values of R here, right? So the Markov chain rules will say that,
like I need to recall Markov chain rules.
Yeah, the Markov chain rules is that if you want to solve this problem, right, where the matrix M is stochastic, column stochastic, we can compute this iteratively. This is what we call the power method as well. So in the power method, we will say that we can compute R at iteration I plus 1 by just multiplying it by M at the iteration I, okay? And we start with the initial one, we can start by giving like the same probability to all the pages or the same repetition to all the pages. So we can say that all of them is having 1 over 3, 1 over 3, and 1 over 3, right? So iteratively, we will compute this value using the Markov chain rules. And we will reach what we call like a steady step, or the stationary distribution, where when you compute this I plus 1, there will not be any change. So we start from 1 until the convergence. We compute this value, Ri plus 1 is equal to m multiplied by Ri, right? So when we reach the convergence, this means that basically we have Ri at each iteration will be equal to m Ri, right? So following the Markov chain rules, this means at a certain point you will have like this stationary points where the computation will not have any change. And then you will reach like the stationary point. Does that make sense?
Yes, awesome.
Yeah, so another thing that you can look is that if you take a look at this formula, it also tells us that R is like the eigenvector of the matrix M, right?
So, sorry, so we will have convergence for the repetition of like Ri plus 1 because like every time we are taking derivatives, right? Or no?
We are not taking derivatives, we're just performing this multiplication. We have the initial state and we compute iteratively, we compute different states, right? By just multiplying the current state, the current value of the matrix by the current state, which is Ri. And
so
we improve
you've written something ends in convergence. What ends in convergence?
Convergence means that when you compute this value for several iterations, it does not change.
Yeah, definitely.
Yeah, it remains the same. So this means that you have reached the stationary state. Okay. Well, so another thing that you can look, which is like, why can we apply this? What is the like the theoretical guarantee that the Markov chain will work? It's just based on the theorem where you have here. If you check a look, you will see that this tells us that R is the eigenvector of the matrix M, right? With the eigenvalue equal to 1. Like if you want to rewrite it as the formula of eigenvector, you have like, it tells us that you have R, let me write it like with the same notation. It tells that if you multiply M by R, it gives you something on lambda R, right? This means that
right. I guess like it's a straightforward equation for this particular matrix.
Yeah. So one way to solve this is that you can either compute all the possible eigenvectors, right? And associated eigenvalues and takes the eigenvector with the highest, with the largest lambda, right? Which in some case will be equal to 1, depending on the property of M. So as M is a positive matrix, it's a squared and positive matrix, right? There's a theorem that shows that if M is a positive matrix, there exists one lambda equal to 1, such that the vector associated to lambda, so if you have R lambda, this vector is unique. So there's only one value, one vector that we can associate to lambda equal to 1. So there's this theorem that tells us, okay, see if we can find this lambda and the vector associated to it, then it is the unique one.
Patrick, just once more.
Yeah.
What does eigenvalues for this M represent? Each eigenvalue, what does it show?
Of which M?
You said it shows some sort of information about our data, right?
Yeah.
About our search results.
Yeah, I mean, like we come up with this equation, right?
Yep.
We come up with this equation. And from this equation, you can see that this tells us this is similar to like an eigenvector. Like it tells that R is eigenvector of the matrix M, based on the definition of what is eigenvector of a matrix, right? And here we can see that lambda is equal to 1. If you took a look here, it tells us that it's eigenvalue with lambda equal to 1, right?
Yeah, that's right.
Yeah. So one way to solving this is like to compute all the possible eigenvectors and then come out with the one that is the highest, with why the eigenvalue is having the highest magnitude. But there's a property that M satisfies, that tells us that we can use some theorems to compute this eigenvector in a straightforward way. Because M, you can see the type of M. All the values are positive, right? So M is a square
Positive,
and
also
positive
diagonal
number.
is 0.
Right?
Also diagonal is 0. I mean, we won't have any loops in our search, I mean, on itself, or we will.
You mean, what do you
When we
mean?
have a bunch of pages, would they have links to itself?
It can happen, yes.
And then
This is,
how the relation, I mean, how R of that particular page would be calculated?
because if A also has like a link to A, you have here what? 1/3, this over 3/3, right? So this matrix will remain column stochastics. Because it is column stochastic, that we can apply the Markov chain to find the value R here by starting with the initial distribution. So yes, indeed, they can have pages that are connected to like loop, like the page connect to itself. Okay.
Yes, okay.
Yeah. So and finally, you come out with the value R that when you reach like the steady point, you give this R as the final result. That makes sense?
So the eigenvector with the biggest value?
Yeah, so R here. So this tells you that based on the property where we have M is a positive semi-defined matrix, right? There exists lambda equal to 1, okay, such that the eigenvector associated with lambda is unique. And this eigenvector will be the solution to our problem, right?
Yeah.
And how can we approach this eigenvector? We can use the Markov chain because our matrix M is also column stochastics.
Yeah.
Yeah. So this is how you can resolve like the PageRank problem. But there's another problem that you may have seen before. It can happen that you have another node, D, okay, which is a kind of dead node. Because when you reach D, you cannot go to any other node, right?
Yes.
So in that case, this will not converge to the global solution, okay? So in that case, this will not converge. So that's why there's another, what?
If we have time, just can you briefly explain me what is a stochastic matrix?
Stochastic matrix is like when you say matrix is column stochastic, this means that each column vectors is like probability distribution. This means that if you sum all the values that you have in each column, they are all equal to 1.
Oh, I see. I see.
Yeah, because this matrix is column stochastic, that's why we can apply the Markov chain.
Markov chain rule is,
yeah, it's like you are looking for a distribution P, right? You suppose that you have the initial distribution where you random, it can be even random, where you randomly assign like a probability to all the possible values, okay? And then you alternatively, you compute this value by multiplying by the matrix that you have and by the previous state. So you have initial state, you update the state by multiplying by the stochastic matrix that you have. This is the probability of moving from one node to another node, okay? So this is the probability. So you have here, oops. So you have here, for example, what is the probability of going from A to A? 0. Probability from going from A to B, okay? From B to A, from C to A. So those are the probability of moving from one node to another node, okay? So this is kind of like your state matrix, okay? And you want to learn this probability distribution, all right? So that's how you can apply that's why you can apply the Markov chain rules to find that stationary distribution. Does that make sense?
Yeah, okay.
Yeah, so what I was saying that we can reach this kind of states where you have one node, which is like a death node. So from this node, you cannot go to any other node, right? So that's why like this formula, we have like updated version where we assume that there's a probability that we can randomly jump from one node to another node, right? And for that, he will try to make this graph a complete graph. So you try to build a connection from one node to all the other nodes, okay? To make the graph like complete. And each node will be associated with the probability of jumping from that node to the other node. So we won't have these zeros anymore in our matrix. But this matrix should remain column stochastic. Okay? So what Google does is that they assume that they have what they call G, which is the damping probability. So the probability that you can randomly jump from one node to another node. And then they will change this formula and we will write it as will be equal to R. It takes our matrix that we have, multiply G by MR, okay? And it adds up 1 minus G divided by N. So the new matrix that you will get from here with the adjacency matrix will be a kind of complete matrix where you have a probability that you can jump from one node to any other node. That will be that will depend on the damping factor G. Okay, so this is another variant that we have like we always converge to the final solution. And this, so here the matrix that will come out from here, or even from here, it will remains like columns stochastic. So we can apply the same procedure to compute that probability distribution. And also, this is what we call the Google matrix. Okay, because it integrates this damping factor, the probability that you can jump from one node to another node. Does that make sense?
And what is N?
So N here is the number of pages. So here we have the number of nodes that you have in the graph. Okay. So for each node, what is the probability that you can jump randomly from one node to another node? It's 1 minus G divided by N, because the graph is complete.
DMR is a matrix itself. Then yes. 1 minus, it's no, 1 minus.
G is a value. This value G is recommended to take it as 0.85. Okay.
True.
Yeah, and then
I mean, it's a constant because I just want to know what is the final output for R. Is it a matrix or it's a scalar? I mean, it should be a matrix, but
a vector, yeah.
This, I mean, on the right-hand side, it doesn't look like a matrix result to me.
Where here?
On left-hand side, we are supposed to get a matrix, right?
Yes. So here, you're supposed to have a matrix here.
Okay, then on the right-hand side, we have a constant adding to some matrix result.
Yeah, it will be element one's addition, element-wise addition.
Oh, so okay, see.
And you can show that, okay, at the end you can have also there will be column-wise stochastics, and then you can apply then the Markov chain to find the distribution. I just here it's more robust because it assumes that the user can randomly jump from one page to another page. So that's what we are going to implement in this lab. So here we have like a set of pages.
Just one more thing, like if we have zero probability on some pages, then when we decrease that value, it will be minus. You know, like we will have negative probability. Isn't it a problem?
You mean where? In this formula?
Sorry, it's addition. I made a mistake. It's 1 minus 0.
It's 1 minus G.
Yeah. Okay. It's fine. Sorry.
Yeah, this one minus G. Yeah. So let's see how we can apply it very fast. Yeah. So we have here a set of pages, right? So these pages can be like, let's say these are the result of a search that you made, and it returns you all those pages. How can you, based on the repetition of each possible answer, okay, answers the query based on PageRank? You got the idea, right? So if there is one page that is having more connection from other pages, this means that so you are giving like high repetition to that particular page. It's like references, okay? Well, so from Wikipedia package, you can load like all the pages. So Wikipedia gave an API for you to load the pages instead of having the API to maybe web scrap or request from Wikipedia. They can even do this for you and pass the pages for you as well. And what we are mostly interested here is that we are mostly interested to the adjacency metrics, right? So let's run this first to get all those pages. So while it's running, information retrieve does not match any page. So this means while there was pages that were deleted. So let's just catch this and ignore those pages. So except just print error loading page. Okay. Again, my IG is highlighting.
I wonder why it gets green.
Yeah, it's weird. Like, I don't know, sometime I need to restart to avoid this wrong passing.
I think you might have like wrong extension activated on your VS Code.
Maybe, most likely. So now we need, what do we need? We need the adjacency matrix, right? So this adjacency matrix is quite matrix where you have one when there's a link from I to G, from G to I, okay? So we take for each pages that we get from the pages that we load the pages from Wikipedia, okay? So if there's a link, so for each link for each pages, we then will do what? We just check if there's a link that in that page, we put like adjacency matrix, okay? So from I to G, we have a link based on the index.
And if we have link again, okay, I see, okay.
Yeah, so we can then pass those pages and build our adjacency matrix. Does that make sense? So
yeah, completely.
We still have
I mean, if you have the code written and we have the output, you don't necessarily need to run the code. So I think it's fine.
Okay, wait. So we want to save also this as a number. Let me see. For link in page error key. Wait, let me restart my IG. I think it's just screwing up. There's no should be any error there. Well, so let me run this again. Load the pages and then we build up the adjacency matrix. So after that, we can dump like the adjacency matrix as a test, okay? We still have the error like. Okay, let me handle this different way for. Data set.
I have a suggestion. Maybe let's just delete that information retrieve from the list up there.
Yeah, that would be the easiest solution. But I don't still understand why it's still indexing it. They should have kept it here.
Maybe you could change it into information retrieval.
I can do what?
Change it into information retrieval.
It is actually
okay.
information retrieval, yeah. Let's see. Actually, it is still let's see. Okay, have it here. Okay. I saw it was still using the page from the list that we got here and we didn't index it, so it makes sense. So after that, we can just like have like you have the adjacency matrix, we dump it as just a text. Okay, so that we can have the text from this text, we can also load from the text to adjacency matrix, right? So we can print this as our adjacency matrix where we have all the links that are connected in between those pages. So next, if we have the list of pages, we have the adjacency matrix. Okay, so we can return the matrix based on the text that we got from adjacency matrix. Okay, and we can load from there as well.
We have the number of the pages, so
yeah, and then we reshape it into a squared matrix. Okay, so this W shouldn't be equal to 40 as we have removed information retrieval somewhere there. So let me just make this pretty much this time. So if you plot it, you can see like the connection. So all those yellow points are the pages that are having connection between them. Okay, so you can see that it is very sparse, right? So it's very sparse. We can like the computation are very straightforward as well. So now we have to do what? We have to prepare the stochastic matrix M based on the adjacency matrix A, if you remember. So you write the code that we divide like columns wise. It is 1 divided by the number of out degree. Okay. But if the number of out degree is equal to 0, we assume that that page, the repetition of that page is like equal for all the other pages. You understand what I mean? So if you have one page from which cannot be reached by any other pages, this means that the number of out degree is 0. You have 0 everywhere in that row, okay? So one way to solving that is we can just remove that row from our adjacency matrix, or we can divide it by the total number of rows. We suppose that this page is connected to all the other pages. Okay, so we give 1 divided by n. So you have to write the code here to compute the adjacency matrix. So from M, so basically you would go for each row. So we take M, can take shape of 1 or 0, as it's a square matrix, it will be the same. So we're going column by column. So we check that the sum of the values, I mean the sum, we check that the row itself is not 0. Okay, this means that this particular node has like out degree different from 0. As we remember, the out degree is the total number of nodes that can be reached from the given node. So if the sum of the out degree of that particular node, so the out degree here will be the out degree of the row G. So if this is greater than 0, then what? Then we can replace this, we can compute this as the current repetition that we have, the current value that we have there, that initially there will be 1 for all the values. That we divide by the total number of out degree of that particular page. So basically, we are spreading out the repetition of that page to other pages, okay? And if it's not the case, we said what? We should add 1 divided by n, okay? So we just replace this value as 1 divided by, the length, the shape of the adjacency matrix. So basically, the node that is not having any out degree, we assume that it is connected to all the other nodes. Okay. So after that, we have the stochastic matrix. Why this matrix stochastic? This matrix will be column-wise stochastic because remember this. This means that if you sum all the values for each columns, okay, it will be equal to 1, as we saw before in the whiteboard, right?
Just there's one issue I don't quite get. So
yeah.
If it's column-wise stochastic, then when we apply the damping factor, it should not be stochastic anymore, right?
If you apply the damping factor?
Yes, because we add some constant to everything, so it basically is not in the range of 0 to 1.
It will still be
the sum of it would add up to some other value, not 1.
You mean if you do this one? So here, not that this is not the damping factor yet. We are just handling cases there we have nodes that are not having any outgoing, node. Okay.
Okay, but for when we have damping factor, it's not stochastic anymore, right?
With damping factor? So when we add the damping factor, we still be stochastic, column-wise stochastic, and we can still use it for use the Markov chain to solve it. Okay.
Okay.
Yeah, we'll come back to the whiteboard later on, and you will see why it will remain matrix stochastic. So is it clear so far?
Yes.
Okay, so well, and then we can plot our matrix stochastic matrix, which is M. Well, you can see that you have those values there. Okay. And you see that where you have 1, when it's 0, it means it is 1. Okay. So when it's 0, you can see that every value all else in the same columns will be equal to 0. So when you have 1 yellow, the entire column is just violet. So they have no values there. Okay. So this tells us that our matrix is also column stochastic. Okay. Does that make sense?
Yeah, I completely get it. I'm like, maybe in next cells I will get some answer to my questions. So let's carry on.
Yeah. So now we have to prepare the Google matrix, right? You remember the Google matrix tells us that we have a damping factor, but you can randomly jump from one page to another page. Okay. So if we open this link, you will see the formula for the Google fact, the Google or the Google matrix. Can you see the browser that I opened?
No, I cannot.
Yeah, of course, because in the chat.
No.
Yeah, so let me just show the browser itself. So here, you have the construction of Google Metrics. You have this formulation. Can you see the browser?
Yes.
Yeah, so here you have this formulation where you have the damping factor alpha that you multiply by our stochastic matrix plus 1 minus alpha divided by n. Okay?
Could
Come again, I can't hear you.
Okay, I see.
Well,
what is alpha?
alpha is our damping factor. It is look at it as the probability that you can randomly jump from one page to another page. Okay?
Okay, got it. Thank you.
Yeah. And also, like, there can be, we do this mainly because if you take the initial graph, there might be dead node there, which are having our degree equal to 0. So when you reach that page, you cannot go to any other page. Okay? But here we assume that we have this damping factor, which will help us to jump from one page to any other page. Because remember, when I have like search result, I can open one tab and open another tab, okay? I can randomly jump from one tab to other tab to explore the result. I will not typically just follow the links that I will get from one page to the next page to the next page. Does that make sense? So this is more robust and it will help us to achieve like good results independently on the type of the graph that we come out in when we build the adjacency matrix. So we have to implement it here. So we have M, we have alpha, okay? So we just have to return what? So based on the formula that we got, we multiply M with alpha, okay? To which we add what? We add 1 minus D, okay? So to have 1 minus D, we need to make it like element Y. So we have to initialize a vector, which we have just one, take shape. Oh, sorry.
I think you won't necessarily need to make one. Just you can apply the constant and it will decrease itself. Well, I'm not sure, but I think it works like that. It's fine.
I think so. I think so. Just to be secure, let's make it like much more explicit. So we have this. Yeah. So we have this minus alpha. Okay. That we divide by. This is minus alpha that we divide by n. What is n here? N is just like the number of columns that we have or number of rows that will be the same. Okay. So after this, we have our Google matrix computed. Okay. Okay. So we can write it differently. Let's make it look more like what we got in the matrix. So we have this multiply. Should be the same though. Okay, so after this, we can have our Google matrix, okay? So if you go to print the Google matrix, you can see that this matrix is still, what can you conclude from the plotting?
I think like this is not actually what I expected, because like I expected if we apply that one, like we won't either have any violet points or we will at least have no yellow points, you know.
We at least have one yellow point.
You know, I assume like when we apply the damping factor, so we can randomly jump from any page to any other page, right?
Yeah.
So we should not have any like we should not have any yellow points, which means there should be no probability 1 in the whole matrix. There should be no value of 1. And there should be no violet pixel, because I mean, there's no probability 0, because we can always jump from one page to another. So there should not be any violet picture. I mean, that's what I assume. I don't know. Is it
Yeah,
correct
but
or not?
you know, when you look at it column wise, okay, this will still remain the property, because you remember the formula. The formula, what we do, you multiply by m by alpha, okay, and then we add up 1. We add up 1 minus alpha divided by n, okay. So we still end up having this column stochastic matrix, okay? But this will integrate the probability that you can randomly jump from one point to another point. So I got your intuition about the fact that we shouldn't have just one everywhere. But if you compare the two matrices, it looks pretty much the same so far.
Yeah, I completely understood why even after damping factor it should be like stochastic still, but I still don't get why we have values 1 after applying the damping factor.
Yeah, intuitively we shouldn't have like to value 1, because you will try to spread that 1 to other pages.
Maybe it's because, I mean, those yellow values, I mean, they represent some high probability, but it's not actually 1, it's something close to it. But I'm not sure.
Yeah. Yeah, I mean, like, it's not actually, it can be like this. Let's try, if we can try to plot this matrix. Let's just see how it looks like if we print G itself.
Maybe print marks.
Print what?
Maximum of the G.
Yeah, you can see that they are not, you don't have 0 anywhere everywhere, but they are very close to 0. So the image,
I guess G dot max. I mean, it's a numpy, right?
also work. Yeah, you can see it's not exactly 1.
Yeah,
okay.
The assumption is sort of true.
Yeah, so if you plot M, you see it's 1, okay?
Yeah, clear.
Yeah.
Very good.
Yeah, so from the image, it looks the same, but not the value is very small, and since they are pixels, it's not visible from our eyes. Yeah. So I will update the links very soon. Don't worry. So how can we solve this? We can solve it in a straightforward way. You have an equation, right? So if we solve this system of equation, we have the value R that we are looking for. That makes sense? So one way of solving it is the most naive way, the most naive approach, but this naive approach is also computationally expensive, okay? So if you go from this formula, how can we solve it using algebraic solution? We can represent it as, let me share the whiteboard again. Not this whiteboard. So we have, this is the Google matrix. Remember, it's the same formula, right? So let me write it properly here. So here we have MR, okay? So we want to represent this just as a system of equation that depend on R, okay? So let's put it big R, so big R such that you see as a vectors when so on. So I can take this here, right? So I will have what? I will have R minus G and R equal to 1 minus G divided by N, right? So I can take R as factor, I remain here with the identity, minus GM, right? So equal to 1 minus G divided by N, okay? So to remain just here by M, I can kind of multiply by the inverse of this one everywhere, right? So if I multiply by the inverse everywhere, so this multiplied by inverse will be identity. I remain with R, and I will have here I minus dm, this inverse, multiplied by 1 minus d divided by n, okay?
But you know, it's a probability distribution, so each vector, so they do not depend to each other. So it does not necessarily have it does not necessarily will have an inverse.
Exactly. This is another limitation of this method. It's like sometimes the inverse may not be computed. Okay. So when it's applicable, we can use this method. Okay. So this assumes that this matrix will have an inverse. The inverse exists. Okay. But still, when it exists, we can solve this equation and have our solution. Okay. So in the next cells, that's what we're going to do. We're just going to compute this value. Okay. So let's come back to the notebook. So in the notebook, I'll just copy the code and paste it, and then we'll run it and see all the result. So resolve it using this. Okay. So it's the same formula. We take the identity matrix minus d multiplied by m. We take the inverse and we multiply by 1 minus d divided by n. Does that make sense?
Yeah, I get.
Yeah, so it's the same formula that we computed there. So, and we have this ranking. So this is how the page will be ranked based on the values that we have from the repetition that we computed here. Okay. Now we can solve this using the power method. You remember the power method?
It's ranked from 0, yeah? I mean, the indexes are from 0, right?
Yeah. So these pages here, how are they going to be ranked? They're going to be ranked based on these indexes, okay? So we'll see later on what those indices looks referred to. So we said that we can also solve them using the power method, the Markov chain, where we have randomly initialized vector that we keep on multiplying until convergence. Okay. So this means that basically we can randomly initialize our first vector. Okay. So we have random values that we divide by the sum of the values that are also normalized. This is probability distribution. Do not forget. Okay. So after having this, we can iterate until convergence. So I can go for like I in range. So I can define my range as, for example, 35 or 36. Okay. So we assume that this is like the number of epoch if you're going in machine learning. So it's iterative process until you have convergence. There's no update anymore. So we assume that up to 35, we're going to have convergence. If not, you can keep on increasing. Okay. And we do what? We just multiply V is equal to our Google metrics multiplied by the current state. Does that make sense? We have guaranteed that this will converge to the solution to this problem. Okay. And that will give us the eigenvalue, the eigenvector of this eigenvalue of this matrix with the associated eigenvalue equal to 1. We have properties that guarantee us that. So we do not depend on whether this is inversible or no. It will always converge. So you see that we have the same indexes, right? So basically they're converging to the same solution, which also proves that this iterative process works. Okay. And to check that,
I didn't get what is this power method.
You remember the power method, the Markov chain that I showed you?
Yeah, you showed me, but I still don't know what is Markov chain rule. So
wait a minute. So when you want to apply the Markov chain rules, it's like if you have a stochastic column-wise stochastic matrix, okay, and you're looking at the distribution of the probability distribution of the columns of that matrix. So the column of that matrix are seen as even. Where you have states from one state to another state. What's the probability for moving from one state to another state? Okay. And you want to compute the final probability distribution. That will give you like the best estimation of the probability that you will find which state is good state than other state, like which state will have the highest probabilities. So let me come back here. So remember, you have this graph, okay? For each graph, you have a probability. Probability from going from share to share. You have the probability from moving from share to share. You have this probability, this probability, this probability, this probability, okay? And we said that we can compute them like this. And it gives us this system of equation where we are looking from R A, R B, and C, which all depend on other variables, okay? And we said that if we take the stochastic matrix, this matrix is column-wise stochastic because the sum of all the columns is a probability distribution, okay? All of this send up to 1. So we can iteratively take random initial distribution and iteratively compute this value until it converges, okay? So when you would
Convert exactly, sorry, I got. So you choose some random probability distribution, I mean,
yes.
something. Then what do you do next? I mean,
next you compute.
Next thing.
Next you compute
what do you
R1,
compare exactly?
You compute R1 as M multiplied by R0, and then you compute R2 as M multiplied by R1, and then you compute R3 by M multiplied by Rn, until you will see that R4 will be equal to M multiplied by R. If the convergence state was 5, you will see that every time that you compute, let's say if it was 3, so every time you have like R3, it's equal to M multiplied by R2 if R4 is equal to M multiplied by R2 if R5 is equal to M multiplied by. This means that this is not changing, right?
Yeah, just one more question. The random probability vector length, it's same as the number of pages?
Yeah, this is same as the number of pages, and this is gives you the probability of among those pages.
So
if you're about to rank, it tells us also the ranking score. So this basically means that all the pages are having the same ranking, okay?
Yeah.
But at the end of the process,
multiply by some random numbers.
Yeah, by initially random numbers, okay?
Yeah.
And remember here, you have the probability of moving from one state to another state, from one page to another page, okay? When you keep on multiplying, you will end up with the So here we're back. So saying that you keep on multiplying until you will reach that steady state where there's no more update. Okay?
Yes. So we multiply every element wisely, all the random probability to the matrix M.
Yeah.
Then we will get some results.
You get some result. You use that result to complete the next step.
Yeah. What's the next step?
The next step is like you compute R1, R2, R3, R4, okay? R1 is what? Is M multiplied by R0, which R0 you initialize randomly. Okay?
Okay, I see.
You compute this as R1, you compute this as R2, okay? And then you compute this as R3. It tells us that this will converge. This R will converge to the final solution.
We will get to some point that like the values of R does not change actually.
Yeah, for example, R5 will be equal to R3. So it's the same value than before. R6 is equal to R3. This means there's not change.
And you have converged. how do we know it will converge? Because you know it's a bit irony, because we are multiplying something by something and we expect it to stay steady without changing.
Because we have this M that's defined as a stochastic matrix. We have this guarantee that we will converge. Okay. And also,
okay.
it will converge to one value of R, okay, which is the eigenvector of this matrix M, okay, and that eigenvector is associated to the eigenvalue lambda equal to 1. Okay, so we have a theoretical guarantee that this will converge to the finite solution. Okay. And mathematically, there's a theorem. This is like the Frobion-Perron theorem, if I recall well, that tells us that if this matrix is a positive matrix, okay, there exists this value lambda, which is the eigenvalue, which is positive. So this means that this matrix, we have only one positive eigenvalue.
I know positive semi-definite, but you also claim that the lambda should be equal to 1, 2. Like there exists at least one lambda which is equal to 1, right?
Yes.
And you mind saying how, or you want to continue on the cells?
How it do?
Yeah, I mean, if you like to, I mean, I do not expect you to give me some answer, but if you can tell me why there would exist some lambda which is equal to 1 in this matrix. If not, you can just continue on the notebook. I mean, I'm okay.
Yeah, I mean that this is like the math. These are the maths behind. Okay, so basically you are showing like we should prove the theorem that is true. So you can do some search before. After that, we don't have time to do that here. So you can do a search to see that there's a proof that this will be having this lambda is equal to 1. Okay.
Okay, fine. Let's continue on the cell, please.
Well, so from here you see that we computed these results. So if we come up with this vector M, this is basically the eigenvector, okay, of the matrix G with the eigenvalue 1. So to check it, we can just compute this eigenvector of G itself, okay? So let's print here. Let's print the eigenvalues and the eigenvectors, okay? And let's see. So you can see that you have eigenvector what? 1, okay? Now eigenvalues, let's just say, and you have
it's eigenvectors.
This is what? The first one is eigenvalue. The second one is eigenvector. So we can even look at the shapes. Okay. So we have all the possible eigenvectors, but if you look at the first one,
the value is 1 for the first one. Yeah.
Yeah. You can see that it's almost 1, right?
Yeah, it's just some double floating point.
Exactly. So if you want to keep up convergence, you can just increase the value, like, yeah. And then you see that the result of this is the same. Basically give us the same result. Okay. That makes sense?
Yeah, it's clear.
Yeah. So which proves all the theory that we built up before. And lastly, we want to print those results. You see that the first page will be like 26 and so on.
We just basically correspond them with the title and just print the title.
Yeah, and just print the title. So this is what we will do here, and then we have those results. Okay. So we see that information retrieval will be the first one, and so on and so forth. Okay.
I see.
So this is based on the stochastic matrix, and this is basically how Google works. But this algorithm is very improved because they will try to, reduce noises. Because if you know how it works, you can basically fake the the model, so they have some improvement to make it more robust and less sensitive to fake pages that can play the algorithm to get like the high rankings. Okay.
Thank you. Thanks a lot.
Yeah, you're welcome.
Like I have already forgotten a lot of basics, and like you basically rebuild again.
Yeah,
Thank
that's fine. That's fine. And I will just ask you connected to like check your attendance. So
Sorry, I'm attending with my phone, so I cannot mark my attendance.
You write your email address in the chat. I will fill it manually. Okay, you can just send your email addresses in the chat. I will fill it manually. Okay. Okay, thanks. Well, so that's it for today. Thank you for showing up. I don't know why your classmates are not attending labs. That's fine.
Thank you.
Yeah, so I will share the notebook now, so you can review it. And if you have any question, just write the text and message.
Could you also please send the recording?
Yeah, I will do so. Yeah. So have a good day. Bye.
Bye-bye.